Hello and good morning everyone. Today inshallah we will start a new chapter. Our chapter today is about eigenvalues and eigenvector. This is one of the important topics that we will study this semester. It's related to the matrices and it's really very important. Of course, all the course resources and the recorded lectures, you will find them on YouTube. And for the main resources, you will find them on Moodle. Also, I shared with you earlier this morning most of the PDFs related to this topic and for the previous week also. The topic of eigenvalues and the eigenvector, it's really handable. The steps are systematic. It needs your focus in the steps 1, 2, 3 in order to be able to get the eigenvalues and the eigenvectors. It contains plenty of stuff or subjects together, working together, the theory of equation, how to solve the matrices, some relations about determinants. Then we will take some new properties related to certain type of matrices, like the diagonalized matrix, how to diagonalize a matrix and so on. So it's really very important. So as I told you, our subject today for this week, today and tomorrow, for the lecture of tomorrow, it's going to be eigenvalues and eigenvectors. Hopefully by tomorrow we will do some exercises on them and you will see it's really very nice. Okay, we will start for the reason for using eigenvalues and eigenvectors. Of course, the applications in STM is enormous. If you try to search or to Google it, you will find plenty of applications where you can use your eigenvalue and eigenvectors. The easiest one, and it's really in front of you, which is better to use, this matrix or that matrix? Which matrix is going to be easier for you to evaluate, for example, to the power of 10? The first matrix or the second matrix? The first, of course, because the first matrix, if you remarked, it's a diagonal matrix. So if you multiply a diagonal matrix in itself, all the diagonal elements will be to the power of 2. If you multiply it in 10 times in itself, all you have to do is to get those numbers, -1, 3, and 2, all to the power of 10, and you will be in. But if you deal with this matrix, you will have to multiply it in itself 10 times, which is not an easy thing to do, especially in matrices in general. So it's much and a way better than using this matrix to handle a diagonal matrix. Are you with me? See? So this is really very important. So two matrices from this definition, we now come to the point of if I have A and B and they are similar matrices to each other. The process of eigenvalue and eigenvector, ya Omar, it helps you to get a similar matrix for this matrix, but on a diagonal form. So you will take advantage from the various properties of a diagonal matrix. So it's really very simple to get B matrix, which is equal to P to the power of -1 times A times P, which is a diagonal matrix. It is possible in some cases, and this is what we are going to study. So if A is similar to a diagonal matrix, then we can take advantage of its properties. That's the bottom line of this slide, and that's the reason of getting eigenvalues and eigenvectors. Okay, what about the exact definition of eigenvalues and eigenvectors? Okay, let A be a square matrix, a non-zero vector U is called an eigenvector of A if and only if there exists a number eta, real or complex, such that the condition is to find a vector and a quantity and the scalar value. To prove this relation, please look to this relation. If I have AU, it's gonna equal to eta times U, where U is a unit vector. It's the vector that we are calling eigenvector. And the A is a square matrix. And the eta is a number which is called an eigenvalue. If you look closely to this relation, it is possible. Because this matrix is a square matrix. Let's say 3 by 3 for simplicity, or 2 by 2. This guy is gonna be 2 times 1. So once you multiply them together, you will have a column 2 by 1. And if you with the same dimension and you multiply it by a number, so it's going to be equal to each other. So now I'm searching for this value, which is called an eigenvalues, and I'm searching for the vector u, which also help in getting this equation to be true. The steps are really very simple. All I have to do, and it's gonna be done once, just to know the equation that we will use. Boss, I will move, شوفي كده يا جودي, I will move eta u from the right hand side to the left hand side. So if you move them, you will have this shape. According to your information about matrices, I can take u as a common from the right. Am I right? So if I take u as a common from the right, you will have a minus eta times I. Of course, you know what's I. صح? What's I? Unit matrix from the same dimension. Times u equal to 0. Omar, if you look to this equation, or to this, if you look to this equation, you have a left-hand side, and it's equal to 0 on the right-hand side. صح, Ms. Salma? So you have two options. If you look closely to this equation, you will have two options. Either u is equal to 0, and that's a trivial solution, because you are searching for u, am I right? So u, it's gonna be zeros. So multiplying it by anything, the result will be 0. So it's a trivial solution. And we already know that u is a non-zero vector. So this is not possible. So the only thing is to happen is having a minus eta I as a matrix equal to the origin. That's the only solution. Based on this, I know that u belongs to the set of r to the power of n, because it's a vector, except 0. And the eta belongs to r. Eta, we will call it the eigenvalues. And for each one of them, there is an assigned eigenvector u, proving this equation. Okay, the steps are going to be as exactly as I told you. A minus eta I is equal to 0, which will lead to, when you have a matrix and it is an origin, or it's a 0 matrix, the determinant of this matrix will equal to 0. Once the determinant is equal to 0, I will be able to solve an equation. And the only unknown that I have is eta. This is called the characteristic equation, which is A minus eta I equal to 0. This is a determinant. So we will expand it and you will see. Okay, solving this equation, we will get the eigenvalues, and resubstituting in this system of equations, I will be able to get u. So once more, bottom line, the steps 1, 2, 3. I will start with getting the characteristic equation. That's the characteristic equation. You will see it right now. That I will get this characteristic equation. Then I will solve it, Judy. What's the unknown in this equation? Eta. I will be able to find it. You will see. It's very, very simple. Once you got the values of eta, it's called the eigenvalues. Step number 2. I will take this value of eta and substitute in this system. That's a system of equations, ya Omar. I will solve this system of equations in order to get the value of u, which is the eigenvector. And then, after getting the eigenvectors, we will be able to get the P matrix, which is responsible about the diagonalization of some matrices. Okay? Okay. I believe we will need to take an example, a detailed example, about these steps. It's really very important. Okay, let's go through this example step by step. I will start with a 2 by 2 matrix, because the steps in 2 by 2 is exactly like 3 by 3. But 2 by 2, it will gather all the ideas, and it's easier to see different cases while we are working. So, I will start with the characteristic equation. Hussein, can you remind me with the characteristic equation? But before we start, that's an ideal question. Remark, you will be subject to have something like this in the second midterm. Omar, I've given you a matrix which is 2 by 2. It's required to find the values, the eigenvalues, and the corresponding eigenvectors. Also, I will need to get an orthonormalized matrix. I will give it to you with this example. Then I will get back to the main slides. Then also, I will need to check this property. It is possible for symmetric matrices. And I will check the proof that I was searching for, that to have a D matrix or the P matrix, the diagonal matrix, which is similar to A, using the U matrix or the P matrix that we saw in the first slide. So let's start step by step. Once more, Mr. Hussein, I will start with the matrix. The matrix is given by 2 rows and 2 columns, starting by 2, 2, 2, and 6. The first step, as I told you, the first step is to find the eigenvalues. How to do this? I will use, yes, you're right, the characteristic equation. What's the characteristic equation, Mr. Hussein? Determinant. And the determinant is equal to 0. What's inside the determinant, Ms. Salma? It's A minus eta times I. Yeah, Judy, I is the unit matrix. So once you multiply by a scalar value, eta, x, whatever, it will appear on the diagonals, or on the diagonal elements of this matrix. Once you do the substitution, the subtraction, between matrix A and this matrix, all you will have to see is this determinant, 9 minus eta, 2, 2, 6 minus eta, and then this determinant is equal to 0. So, then the second step, what's gonna be? I will try to expand, Mr. Adham, this equation, it's an equation. Try to expand the determinant. Huh? I will multiply 9 minus eta times 6 minus eta. So it's going to come up to 9 minus eta times 6 minus eta minus 4 equal to 0. Any questions? Any questions? Okay. All I did, I have tried to expand this determinant, which is a determinant 2 by 2. So I got the multiplication of the elements of the principal diagonal minus the multiplication of the elements on the principal diagonal. Then I will solve this equation. Omar, start getting this quadratic equation. Negative eta times negative eta is gonna be eta squared. Then negative 6 of eta, negative 9 of eta, which is gonna come up to negative 15 of eta. 9 times 6 is gonna be 54 positive. Minus 4, so you will come up to 50 in positive. Am I right? Equal to 0, which can be factorized. Okay? To eta, let's say 10, 5 minus equals 0. Now I have the values of eta, which is 10, and the eta 2 is equal to 5. Am I right? These what are the values of the eigen values relative to this matrix. For each one of them, for each one of these eigenvalues, I will need to find the corresponding eigenvector, which is U. How to find U? I will substitute in this system or homogeneous system. That's a matrix, am I right? And that's the unknown elements, U, and it's equal to 0, which means it's an homogeneous system of equations. Let's do substitution. I will start with getting U1. The first vector, which is U1. I will symbolize it by this way. I can call it X, I can call it U, I can call it V, whatever. I will call it U1, which means the first vector. Okay, which corresponds to the first eigenvalue, which is 10. So now, start substituting in this equation. How it's gonna be, Mr. Omar? Leave your fingers. It's gonna be an augmented matrix. This augmented matrix. And I will subtract the elements of eta from the principal diagonal. So simply, it's gonna be 9 minus 10. Then I will have 2 and 0. For the second row, Salma, it's gonna be 2. Then 6 minus 10 equal to 0. Any questions for this step? I made a substitution, direct substitution. Look, Ms. Salma, to the system. A minus eta, you already know it right now, times I in U is equal to 0. So that's the matrix A minus the value of eta, which is 10, times the unit matrix, so it will affect only the principal diagonal, and it's equal to 0. Now I need to solve this system. Judy, solving this system will give you what? Will give you the components of the vector U. صح? That's the first component, and that's the second component of this vector. Okay, let's do it. In order to solve it, I will need to reach a reduced echelon form. Okay, if you remark, it's really very simple, because you will have the pivots and the elements like this. 9 minus 10, 1. Then I will have 2, then 2 and 4, and it's equal to zeros, as you can see. If you look closely to this matrix, you will have either 2 identical rows or 2 rows with a ratio connecting them together. So all I have to do is to multiply the first row -2 and add on the second row to get my reduced echelon form. If you do so, you will have the following. If I did this, I will have the following. This is 1, that's gonna be 2 and 0, then 0, 0 and 0. Am I right? So once more, it's a 9 minus 10, which is gonna be, it's gonna be 9 minus 10 is gonna be a negative over 1. Then I will have 2 and 2, then 6 minus 10, which is gonna be a negative over 4. Multiplying in 2 and adding, you will have this relation. So now I can put U1 sub 1, which is equal to, just step by step, let me do it step by step. This is U sub 1, and this is U1 sub 2. And once you start substituting, I will have the following. 1 times U sub 1, negative 2 U1, second component, and it's equal to 0. So once more, I have the value of 10. I start substituting, so it's a 9 minus 10, it's going to be negative 1. 2, 2, 6 minus 10, it's going to be negative 4. That's the matrix. Remark, at this step, you will have either 2 identical rows or there is a ratio connecting these rows. Okay, there is already. If I multiply the first row in 2 and add it on the last row, all the last row will disappear. And you will have the first row with the pivot is equal to 1. That's the reduced echelon form. Are you with me, Salma? Now I will need to expand it. I know that the first vector, U1, consists of 2 components, U1 sub 1 and U1 sub 2. It's a vector in 2 dimensions. So how many components it should have? 2 components. The vector number 1, first component, vector number 1, second component. Those are the 2 values, U1 sub 1, U1 sub 2. Start to expand this equation. It's going to be 1 times U1 1, then negative 2 times U1 2, which means that I have U1 first component equal to twice, okay, the second component. Now I can substitute in order to get the span of the eigenvectors. It's really very simple. I notate once more that U1 is equal to 2 components, U1 sub 1, U1 sub 2. I will use this relation. So this is 2 U1 sub 2, and it's a function in U1 2. It's an infinite number of solutions. Choose any value for U1 2, any value that you like. I believe choosing 1 is very nice. So if you put U1 2 as equal to 1, you can choose any number. Because it's an infinite number of solutions, it will depend on the value of U1 2. Okay? Step by step, I will take U1 2 as a common, and I will have 2 and 1. Now, if you put U1 2 is equal to 1, the first vector, it's gonna be 2 and 1. That's the first vector. So, for this matrix, the first eigenvalue is 10. and the corresponding eigenvector will be, that's the span or the basis of this eigenvector space. I will redo the steps. But now, while we are redoing these steps, I will use exactly the same steps, but with eta. Now I'm getting U2. Now eta will be equal to 5. Redo the same steps. Okay, once more. It's gonna be, حد يقول لي 9 minus 5. Oh, 9 minus 5, 2 and 2, then 6 minus 5, and this is zeros because I'm substituting in this values. The second step will be, it's gonna be 9 minus 5, it's gonna be a 4, and that's 2, and that's a 0, that's a 2, 6 minus 5 is 1, and it's equal to 0. Still, Miss Judy, you have a relation, or they are exactly the same. I'm talking about the two rows. Okay, now if I multiply the first row by negative half and add it on the second row, it's going to be like this. 0, 0, and 0. Then I will divide on 4. So I will have 1, then 0.5, and it's equal to 0. That's for the elements of the first row. Any problem? That's the reduced echelon form. Once more, I'm speaking about, or we are talking about, the second vector, first component, the second vector, second component. Am I right? Start to expand them. So once more, I will have a relation connecting the second vector, first component, with the second vector, second component. And both of them equal to 0. Which means U2 sub 1 is equal to minus 0.5 U2 sub 2. That's the first component in a relation of the second component. Once more, Omar, I will substitute. So I will have U2, which consists of U2 sub 1, U2 sub 2. Now start substituting. I will replace the first component by negative half. So it's going to be a minus 0.5 U2 sub 2, and that's U2 sub 2. Choose any value for U2 sub 2. Any value that will give you integers, that will make your life easier. I would suggest that U2 sub 2 is equal to 2. I will choose 2. Why to choose 2? Because I will get rid of the half that I have. So simply, I can say that U2 is equal to, if you put U22 is equal to 2, you will have negative 1 and 2. Am I right? صح? Okay. Now I have the second eigenvector. So the steps, as you can see, it's really very simple. I will make a substitution, solve an equation, getting the values of the eigenvalues. I will take each eigenvalue and substitute, Ya Omar, in the system of equations. I will have a system, and I'm searching for the components of the eigenvector. I will be able to grab it. Once you have a number of vectors relative to the number of eigenvalues, now I can get the B matrix, which is required for similarity, as you will see. Okay, once more. This is the problem that we were talking about, 9, 2, 2, and 6. The first step that I will do, I will use the determinant. So I will make the substitution. It's really very simple. 9 minus eta, 2, 2, 6 minus eta equal to 0. Second step, I will try to expand it. You will end up, Mr. Ahmed, having a quadratic equation, which is eta squared, negative 15 of eta plus 50 equal to 0. Solving this, you will get two values, 5 and 10, or 10 and 5. If you remark, Salma, I've considered the eta 1 is equal to 10, and the eta 2 is equal to, while on the slides, you will see that I'm considering eta 1 is equal to 5, and the eta 2 is equal to 10. So I've replaced them. Do you think it will make a difference? No. Yes, you are right. So the second step, now we will solve the homogeneous system of equations that I told you about. And once you are solving this system of equations, you will be able to get your eigenvalues. Vectors. So once more, that's the system. I will start substituting Omar by 5. Now I will have two identical, or there is a relation between these two rows. I will multiply the first row by -½ and add it on the second row. Then divide on 4. There is a typo here. This is supposed to be, no, it's okay. I believe it's correct. The typo will come in here because 1 times u11, it's u11, and this is going to be a 0.5 u12. Then u11 is equal to -½ of u12. The second step, I will make the substitution. Then I will substitute instead of u12 by 2. Then you will have u1, which is -1 and 2. Similar steps will be done for getting the second vector, but with the value of 10, as you can see. Similar steps, exactly the same. I will get the relation connecting u21 by 2u22, which means one of them is twice the other. Then I will make the substitution, as you can see. Now I have the vector, which is 2 and 1. There is a number of remarks which is really very important. I will put them now. I need to define what's called an algebraic multiplicity. Can you repeat it? Algebraic multiplicity. What's the algebraic multiplicity? It is the number of repetition of vectors, of eigenvalues. If you remark, Omar, once we solved this equation, I had two numbers, two distinct numbers, am I right? Which is 5 and 10. Both of them repeated once. So I have 5 as a root and 10 as a root. So the algebraic multiplicity of 10 is 1, because it's repeated once. The algebraic multiplicity of 5 is also 1, because it's repeated once. This is called, Judy, algebraic multiplicity. There is also another very important definition, which is geometric multiplicity. Geometric multiplicity. What's the geometric multiplicity, Miss Judy? It is the dimension of the eigenspace. The dimension of the eigenspace. What's the dimension? If you look, Miss Judy, you will find this eigenvector. It has a general form, which is -1 and 2. We call it basis of the eigenvector space. How many vectors in here? How many vectors in here? So the geometric multiplicity is equal to 1. It's the dimension of the eigenspace. Ya Omar, also, once more, how many vectors in U2? Ended up having one vector. So the basis of this eigenspace is 1. Now I have the algebraic multiplicity equal to the geometric multiplicity. So this matrix is diagonizable. So I can get a diagonal matrix similar to this matrix. Okay, once more. Adham, what's an algebraic multiplicity? It is the number of repetition of the eigenvalues. يعني تكرار الايجنvalues. معايا مستر أحمد؟ What's the geometric multiplicity? The number of vectors لكل eigen vector. السبيس بتاعه. هنا أنا عندي كام vector for the first vector؟ 1. يبقى الدايمنشن بتاعه كام؟ 1. يبقى الالجبريك multiplicity is equal to 1 and the geometric multiplicity is equal to 1, so it's diagonizable. What's the second step? I will get the also normalized nodal matrix. I will take the first vector, okay, according to my calculation, we'll take the first vector and the second vector. The first vector will be the first column. The second vector will be the second column. Do you read me? If you remember, while I was evaluating this guy, I've considered u1 sub 2 is equal to 1. And when we were talking about this guy, we considered u2 sub 2 is equal to, and I can use any number, am I right? In order to generalize our solution, I will need to get a unit vector from vector number 1 and from vector number 2. How to get a unit vector from a vector? Any ideas? How to get a unit vector from a vector? All I have to do is to divide the components, Ms. Salma, on the magnitude of this vector. طيب أدهم, what's the magnitude of a vector? It is the square root of the sum of squares of its components. يعني معنى الكلام Mr. Ahmed, I will take the first vector which is negative 1 and 2, صح? Square the first component which is gonna be 1 plus square the second component which is gonna be, add them together which is gonna be under square root. So I will divide these two numbers, okay, the first column on root 5. Then I will go for the second vector, which is the second eigenvector. Doing the same, Ya Omar. I will square the first component, plus I will square the second component. Adding them together, which is gonna be, it's just a coincidence here. So the sum of them is 5, under the square root. So the matrix that I'm looking for is this matrix, where the first column, the first eigenvector, normalized, and the second vector, the second eigenvector, but normalized. How to normalize it? Divide by the magnitude. Once more, Hussein, what's the magnitude? It is the sum of the squares of the components under square root. So we'll take the square root of the sum of squares. Okay? There. شو بس سهل. This matrix, why when you are dealing, Ya Omar, with a matrix from the beginning, which is a symmetric one, that's a symmetric matrix, am I right? The elements are symmetric around the principal diagonal. Then your eigenvectors will be orthogonal. Yes, Ms. Salma. How to check if you have vectors orthogonal? If you multiply them together, dot product, the result will be 0. بص كده Mr. Ahmed. Negative 1 times 2, negative 2, plus 1 times 2 is equal to 2. The sum of them is equal to 0. So these two vectors are orthogonal. Orthogonal, it means perpendicular. يعني two vectors دول عاملين كده. معايا يا شباب؟ Okay. طيب when you have a matrix and its columns are orthogonal in each other, it's called an orthogonal matrix. The orthogonal matrices has a wonderful property, which is their inverses are their transpose. So simply, this matrix, its transpose, is the inverse of this matrix. Can you imagine? So if I have this matrix, if you get the transpose, making the rows to be columns and the columns to be rows, then it's the inverse of this matrix. I cannot check this property. So that's the main matrix. That's the matrix that I had from the eigenvalues. Okay, I will get the transpose of this matrix. That's the transpose. Then, Mr. Adham, if you multiply them together, you should have the unit matrix. Because I told you, if this is an orthogonal matrix, then the transpose will be the inverse. It's really very easy to check. بص كده Mr. Ahmed. That's the U transpose, which is the inverse. If I multiply it by U, then the result will be a unit matrix. بص Ms. Salma, negative 1 over root 5 times negative 1 over root 5, it's going to be 1 over 5. 2 over 5 times 2 over 5, it's going to be 4 over 5. Adding them together, you will have 1. Up, step by step. That's the multiplication. If you get the addition, you will have your matrix, which is 5 over 5, 0 and 0, 5 over 5, which is going to be 1, 0, 0, and 1, equal to the left-hand side. That's the first check. Also, I will be able, this matrix, it is the matrix responsible about the diagonalization. Look to the wonderful property that you will have. Now I can get D, which is similar to A, okay? And the D is a diagonal matrix with the eigenvalues as the elements of the principal diagonal. So if I got U transpose, which is the matrix that I had its inverse, times A, the given matrix, the matrix that I started my solution with, multiplying it by U, the result will be a diagonal matrix. And this diagonal matrix, if you do the multiplication, I multiply this matrix by that one, this is the result. Then I will multiply the result by the last matrix. That's the multiplication. That's the addition. And the result is amazing. What's the value on the principal diagonal? The first eigenvalue. I've used here, which is fine. What's the value of the eigenvalue on the element 2, 2? It's the second eigenvalue. Now I had a diagonal matrix, similar to the original matrix. Okay? Having the eigenvalues as elements on the principal diagonal. معايا Mr. Hussein? So I can take the advantages of dealing with diagonal matrix instead of dealing with a whole matrix altogether once more. If you remark in this example, we already knew how to get the eigenvalues, am I right? And then substituting and solving how to get the eigenvectors. Then also we remarked the condition for orthogonality between vectors. If you multiply the components, the sum will equal to 0. That's if your original matrix is a symmetric matrix. This is remark number 1, am I right? I can get the matrix which is responsible about the diagonalization, which is U matrix, this matrix. How to get this matrix? I will take the first vector at the first column, the second vector at the second column. I will normalize these vectors. How to normalize them? I will divide every vector on its magnitude. What's the magnitude? The square of the sum of the squares of components. Now I have the U matrix. It's an orthogonal matrix. Mr. Hussein, how to check it is an orthogonal matrix? If you get its transpose and you multiply them together, you will have the unit matrix. Okay? That's the check that we did. The last remark. Of course, this matrix can get a similar matrix where the elements on the principal diagonal are the eigenvalues. صح?